We're now going to study the topic of related rates. Now, oftentimes in fields of science and engineering, you'll have two related variables like an x and a y that are changing with respect to a third variable, oftentimes time t. And you will know the rate of change of one of the variables, like let's say you might know x prime of t, and you'll want to find the rate of change of the other variable, so you'll want to find y prime of t. Now to find y prime of t, you'll need to find an equation that relates x and y. You can then take that equation and differentiate it with respect to time t, and then you'll be able to solve for y prime of t. For example, here's a little graphic down here illustrating an application. We have here a piston that is connected to a crankshaft. Right here's the crankshaft with a connecting rod. And suppose that we know that the crankshaft is turning at a certain rate. So we may know theta prime of t. Suppose, for example, that theta prime of t might be 50 pi radians per second. So 50 pi radians per second would be 25 revolutions per second, since 2 pi is 360 degrees, one full revolution. So we may know theta prime of t, and we may want to find how fast the piston is sliding up and down the cylinder when theta is a certain value, like perhaps pi over 2. So you may want to find x prime of t when theta is pi over 2. So what you would have to do is you would have to find an equation that relates theta and x, and then differentiate that equation with respect to time t, and then solve for x prime of t. For example, we have, as you'll see in this little graphic here, you may know, see the theta is turning, so we may know how fast the theta is changing, and then we want to find how fast this piston is sliding up and down when theta is pi over 2, for example, like when theta is right about there. Say theta is right there is pi over 2, we may want to know how fast this piston is sliding up and down. There's a good reason why an engineer might want to know that. It might be related to the wear of the cylinder in some respect, or perhaps this is connected to another piece of machinery and you have to know how fast that other piece of machinery is then going to move. Now let's take a look at a simple example to start. We're not going to do, this is somewhat of a complicated example. Let's start with a simple example first to illustrate how we can find a related rate. So in this example, we have a particle that is moving along this curve, y equals x minus 1 cubed over 3 plus 1, in such a way that the rate of change of its x-coordinate, dx dt, is always 2. And that would have units of whatever, feet per second, meters per second. We're not specifying here exactly what the units are. Now, we want to find the rate of change of y, find how fast y is changing when x is equal to 3, that's for part A, and then find the rate of change in y when x is equal to 1, and then we'll compare the two answers. Now down here we have a graphic illustrating what's going on. So we have, here's our particle right here. It's moving along the curve, that's the curve y equals x plus 1 cubed over 3 plus 1, in such a manner that its x-coordinate right there is moving in this direction with a constant speed of 2. So every second, perhaps, it will move 2 units to the right. Now, we want to ask ourselves, here is the y-coordinate of that point. It's the little green dot right there on the y-axis, and it will be moving upward. And we want to know how fast is it moving upward when the red dot is at location 3 and then at location 1. So let's watch this in motion here. We'll set this in motion and you'll see what's going on. Okay, so you see the red dot is moving to the right at a constant speed. Maybe I'll slow that down a little bit. So you see the red dot is moving to the right at a constant speed, and the green dot right here, that is moving at a different speed. You see right here it sort of slows down, stops, and then it continues upwards. So its velocity is different from the red dot, and we want to find the velocity of the green dot when the red dot is at 3 and at 1. So that's what this problem is asking us to do. We're trying to find the velocity of that green dot. Alright, so let's see how we can do that. So we're going to assume that x and y are both functions of time t, and we need to find the rate of change of y. Now, as soon as you see that wording, you need to look for special wording in these problems. Rate of change means you want to find dy dt. So we want to find dy dt. And assuming x and y are both functions of time t, and that they are related by this equation, we'll then be able to find dy dt. So let's start with this equation. And we're assuming y is a function of time t, and so is x. Now, if we want to find dy dt, we have to differentiate this equation with respect to time t. So let's do that. Now we see this piece right here, of course, is 0. That's the derivative of a constant. So we need to find the derivative of this piece right here. This side is dy dt. That's what we need to find, so we'll just leave it over here. Now, to differentiate this, we're going to have to use the chain rule. We're going to have to first differentiate with respect to x, and then multiply by dx dt. So we're going to do this. So you see we just applied the chain rule here. Notice how those dx's, you can think of them as canceling, and you just recover d dt of what we started with up here. So that tells you that you are using the chain rule correctly, if you can do that cancellation like that. Now let's evaluate the derivative of this piece right here. We're just differentiating this with respect to x now. Now notice we can move that 1/3 out, and we have And now to evaluate this piece right here, we just have to do a little application of the chain rule. We have to differentiate with respect to the inside, which is x minus 1. So this is going to be 1/3. I differentiate with respect to the inside here, so I drop the 3 down, times the inside squared. And then I have to differentiate x minus 1 with respect to x. That's just 1, right? So that's what I meant by just being a little application of the chain rule there. And then we still have our dx dt right here. And so therefore we have that. And there we go. We have found what dy dt is in terms of x and dx dt. And now we can answer the three parts up here. For part A, we want to find dy dt when x is equal to 3. Now, that's going to be, and we'll indicate that the x is equal to 3 like this, when, that's what that little line means, when x equals 3. And that is going to equal, now we'll put the 3 in for the x up here. And so we get 3 minus 1 is 2 squared times, and the dx dt, now we were given that that was 2 up here, right? So we can put 2 in there, and we get 4 times 2, or 8. So the dy dt, or the y, is changing at the rate of 8 units per unit of time when x is equal to 3. And for part B, dy dt when x equals 1, well, if we put 1 up in here for x, you see we get 1 minus 1, that's going to be 0. So its velocity or rate of change is 0 when x is equal to 1. And then for part C, just comparing the answers, well, we just see that at this point in time when x is equal to 1, it looks like the y component will come to a stop. Its velocity, it stops for an instant. Whereas when x is equal to 3, the velocity of the y component is 8, which is actually faster than the velocity of the x component. Now let's take a look at the graphic here and see why these two values make sense. If we watch the graphic here, you'll notice that right when the red dot passes 1, notice how the green dot comes to a stop. That's indicating part B down here. dy dt when x is 1 is equal to 0. Watch that again. The green dot will come to a stop right when the x passes 1, and then it continues. Now when x is equal to 3, when the red dot passes 3, the green dot is actually going faster, 4 times faster than the red dot. Now it doesn't look like that from the graphic here, but that's because the scaling of the y-axis here is different from the scaling of the x-axis. You notice the x-axis from this point to this point goes from 0 to 4, whereas the y-axis goes from 0 up to about 12. So the scaling is off. That's why it doesn't look like it's moving faster, the green dot is, but it really is moving faster when the red dot passes 3. All right, so that's how we do a related rate problem. We were given this equation. We wanted to find dy dt when x took on certain values, and so we just differentiated the equation with respect to t and solved for dy dt. Now there's one other key thing to note here that's very important, and we're going to look at this, will be part of our guidelines. Notice how we found dy dt before we plugged these x values in. You never plug any numbers in to your equation until after you differentiate everything. That is critically important. You do not plug numbers in to your equation until after you differentiate. The only time you may plug numbers in is if you know those values never change with respect to time. Then it's okay to plug them in. But these values, the x values, are changing with respect to time, so we cannot plug these in until after we differentiate. Also, one other note here, I wrote the dy dt as x minus 1 squared times dx dt. At this point right here, we could have plugged the number 2 in for the dx dt since we know it's always 2 up here. We did that down here anyway, but we could have written this as 2 times x minus 1 squared as well. So it's perfectly fine to put the 2 in there for the dx dt and say dy dt is equal to this value here. We did that down here anyway. Alright, now let's take a look at some guidelines for solving these related rate problems. So here are some guidelines that we can follow when solving related rate problems. The first thing you want to do, if appropriate, is draw a picture illustrating the problem. That's usually what you want to do for most math problems. Second, label all variables related to the problem in your illustration, both those that are given and those that need to be found. Then step 3, identify given quantities such as derivatives of variables that are labeled in step 2 and identify what needs to be found. This will usually be a derivative of one of the other labeled variables. Step 4, find any appropriate equations that are relating the variables in step 2. For many of the problems that we do, these will be equations from geometry like the Pythagorean Theorem, similar triangles, area formulas, volume formulas, equations from trigonometry, etc. Step 5, using the chain rule, differentiate the equation or equations that you found, and you'll usually do that with respect to time t. And then step 6, using the differentiated equations, solve for the desired variable. This will usually be the derivative of one of the labeled variables. That's usually what you'll be solving for, is another rate of change of one of the other variables. All right. Now, there's one very important thing to note here. When you're performing step 5, when you're differentiating, you do not substitute any constants in the equation to be differentiated until after you've differentiated the equation. For example, in the previous problem we did, we were told to find dy dt when x was 3. We did not put the 3 into the equation until after we differentiated it. Now, it is okay to substitute constants into the equation if the constant represents something in the problem that never changes with respect to time. For example, like the height of a lamp post. The lamp post, that height will never be changing. So it's okay to put that into the equation. Or in another problem we'll see, we'll have the length of a ladder. We're assuming, the ladder doesn't change its length. So it's okay to put the length of the ladder into the equation if it doesn't change with respect to time. Now let's take a look at a few examples. So here we have a ladder problem. We have a 25-foot ladder slides down the side of a house in such a way that the base of the ladder is sliding outward at the rate of 3 feet per second. We want to find the rate at which the top of the ladder is sliding down the wall of the house when the base of the ladder is 15 feet from the wall. So following our guidelines, let's first of all draw a picture representing this problem. Now over here we do have a graphic, so this is already drawn for us. Now what we have for this problem is we have a ladder here, and the base of the ladder is sliding outward and the top of the ladder is sliding down, so something that looks like this. Okay, so you see the base is sliding outward, the top slides down, and we want to find how fast the top of the ladder is sliding down the wall of the house at a particular point when the base is 15 feet from the wall of the house. So this is our picture, and let's label the variables. So we will call this point right here, we'll call that x. on the x-axis, and that actually represents the distance from the base of the house. The house is right here, by the way. Now, this is the house here. This is the wall of the house. So this distance is x, and let's label this point right here as y. And now we're given that the x, this point, is moving outward, so the x is changing at the rate of 3 feet per second. And we want to find how fast the y is changing, or how fast this point is moving down the side of the house. So that's what we need to find right there. All right, and let's see, what else do we have to label? Oh, well, the ladder is 25 feet long, so we could label that as 25 right there. All right, now let's identify what are we given and what do we want to find. Well, we are given dx dt is 3 feet per second. So we're given that. We're also given the ladder's 25 foot long. We already have that labeled. And let's see, what do we want to find? We want to find dy dt when x is 15. All right. Notice one thing here. We want to find dy dt. Where did we pick that out from here? Well, notice the wording. Find the rate at which the top of the ladder. As soon as you see that word rate, that tells you you're looking for a derivative. The word rate, derivative, synonymous. Now, we need to find some equations that relate x and y. So, well, let's see, looking at this picture here, I see a triangle, right? See this triangle right here? And we need an equation that relates the x and the y. Well, just notice for this triangle here, the base here, that distance is x, right? This point is x, so that means the distance from here to here is x. And the height of the triangle here, that's the y. Right, because this point is y, that means this distance is y. So now we see we can get an equation that relates x and y, the Pythagorean Theorem. So we know that now x is going to be a function of time t, and I'm going to square it, plus equals 25 squared. Now we can differentiate this equation and find what dy dt is in terms of dx dt and x, and then we'll be able to solve our problem. So now differentiating this with respect to t, now this of course is 0 here. Now when we differentiate this part right here, this is going to become 2x times dx dt, or 2x x prime. Now that x prime, remember, that means dx dt. And then this part right here is going to become 2y y prime. And the y prime is what we want to find. The x prime we're given as 3 is equal to 0. And once again, if you're a little confused on how do I get 2x x prime here, well, what we're doing here is we're using the chain rule. Okay, so when we look at just off to the down here at the bottom, note that we have to use the chain rule. This is d dx of x squared times dx dt, right? Notice how those dx's cancel, and you recover d dt of x squared, which is what we have over here. This part right here is 2x, and this dx dt is your x prime. And the same thing for 2y y prime. All right, so that's how we got those terms. And now we just need to solve for y prime. So we'll take the 2x prime over to the other side. The 2's, of course, will cancel. We can divide this y to the other side, and we will get y prime. There we go. Now we need to solve for y prime when x is 15. We're also given that x prime is 3, right? This is the dx dt. So we're given that this is 3, so we could put a 3 in here for the x prime. That right there is 3. And so we can simplify this as negative 3x over y. And now, y prime when x is 15. Notice we do not plug the 15 in until after we've differentiated everything. So we get y prime when x is 15 is going to be negative 3 times 15 divided by, well, now we need to find what y is. We're not given what y is. Well, from this equation up here, from our equation x squared plus y squared equals 25, we can solve for the y. So note that just off to the side here, when x is 15, y is going to be the square root of 25 squared minus 15 squared. That comes from right up here. When you put the 15 in for the x, you can then solve for the y. So taking the 15 squared over and then taking the square root, you get what y is. And so what we get here then is our answer, which is negative 45 divided by the square root and that can be simplified as negative 45 over 20. 20, that just happens to be the square root of 25 squared minus 15 squared, and this is negative 9/4, or negative 2.25. And that will have units of feet per second as well. So then we have our answer over here, y prime of t when x equals 15 is negative 2.25 feet per second. And that is our answer. Notice that the negative 2.25 makes sense because the top of the ladder is sliding down the wall. It's coming back to your the point where you're measuring from. So it's coming towards the bottom of the house, so it makes sense that it should be negative 2.25, whereas the base of the ladder is sliding away from the bottom of the house, and so it has a positive velocity. So that makes sense. And notice one other thing, whenever we write x prime and y prime, in particular the y prime, that does not mean dy dx, that means dy dt in this case now. So these are all functions of time t here, right? So just make sure you understand that. These are all dx dt, dy dt. We're always differentiating these problems with respect to the third variable, t, normally. All right, let's take a look at this, and we'll let you work on one. Now, if you'd like to, you can read through this problem and try this one on your own. Assuming you've done that, let's go over the answer. So we have a boat is being pulled towards a dock via a winch on the top of the dock. The winch winds in rope at the rate of 2 feet per second, and it is located 8 feet above the boat deck. Find the rate at which the boat is approaching the dock when the boat is 20 feet from the dock. All right, so the first thing we want to do here is draw a picture. So now my artistry isn't that great, but so we have a winch up here. We have our water here and our boat. And we have a rope connecting the winch to the boat, and the boat is coming in towards the dock. The rope is also being pulled inward this way at the rate of 2 feet per second. And we have that this distance here, we have a little triangle being formed here. This distance is 8, and that's the distance from the dock to the boat. Now let's label some variables here. Now this height we know is always 8. That's always 8. Let's call the distance that the boat is from the dock, well, let's call that x. And that's going to be a function of time t. And let's say the amount of rope that we have out at any time t is s of t. All right. And so there we go. We have everything labeled. Looks like we have another triangle here, so it looks like we might bring into play the Pythagorean theorem again. Now that we have our picture drawn, our variables labeled, let's see what we're given and what we want to find. So we are given, well, it says the winch winds in rope at the rate of 2 feet per second. That tells us how fast this s is changing with respect to time t. You see the key word there is rate. So we're given ds dt is negative 2 feet per second. It's negative because the rope is being wound inward. Notice this point right here is approaching the winch, so the velocity is going to actually be negative 2 feet per second. So we're given ds dt equals negative 2, and that has units of feet per second. And we're given that the winch is 8 feet above the deck of the boat. We have that labeled here anyway, so we don't need to write that down. And we want to find dx dt when the boat is 20 feet from the dock, so when x equals 20. All right, so we have everything drawn. We wrote out what we're given and what we want to find. And now we need to find an equation that relates x and s. Also notice one thing that I didn't mention. The dx dt, once again, notice this word rate right here. Find the rate at which the boat is approaching the dock. That immediately tells you you're looking for a derivative. Now the equation that relates x and s, well, we see a right triangle here again. And so it looks like we want to use the Pythagorean theorem. So we want to use so there we go, Pythagorean theorem. X squared plus 8 squared equals s squared. Now we have to differentiate this with respect to time t. So this term, of course, is just 0. And now when we differentiate this, we're going to get 2s s prime. Now remember that s prime is s prime of t equals, and this is going to be 2x x prime. And that, of course, is x prime of t as well. And once again, notice when you're going, the reason we got 2s s prime down here is because we need to use the chain rule on this part, right? So just off to the side here again. we have to write this as all right, this is the chain rule. Notice how these ds's, they cancel, and so we get d dt. We recover what we have here, and this part right here is 2s, and this part right here is our s prime of t. All right, now let's see. We are given the s prime. We want to find the x prime. So let's isolate the x prime on one side. Notice we can cancel those 2's, and we will get, I'm just going to flip this around, we're going to get x prime equals 2, sorry, not 2, just s prime divided by x. And now we want to find x prime dx dt when x is 20. So x prime when x equals 20. Now we do know that the s prime, we are given the s prime here is -2. So we can put that in. So we're going to get the s prime is -2. The x is 20. Now, we're not given what s is. Well, once again, we can go back to our Pythagorean theorem here, and we can solve for x, or solve for s when x is 20. So if we just put 20 in for x, we'll be able to solve for s. So s is going to be, when x is 20, s is going to be the square root of 20 squared plus 8 squared. All right, I just put this 20 in here for x, and then took the square root to solve for s. So there we go. And then this simplifies as -2 root 29. This is what you would get if you would simplify this all the way down. Divided by 5. And if you use your calculator, that is approximately -2.15, and that would have units of feet per second. Since everything else here has units of feet and seconds, we're going to retain the units of feet per second. And there's our answer. -2.15 feet per second. Notice the negative makes sense because the boat is approaching the dock. So since it's coming towards the dock, which is the location where you're measuring from, your velocity is going to be negative. If it were moving away, your velocity would be positive. So always check that out. That lets you know if you've done things correctly. All right, let's take a look at another problem now. Now, if you'd like to, you could try this one on your own. Let me give you one hint, though, if you're going to do that. You'll need to use the volume formula for a sphere of radius r is, all right, so that's the volume for a sphere of radius r. So given that, try to do this problem on your own. Now, assuming you've paused the video and done that, let me go over the answer. So we have here a spherical balloon that's being filled with air, and the air is being pumped in at the rate of 5 cubic inches per second. We want to find the rate at which the radius of the balloon is increasing when the radius is 6 inches. So let's draw a picture here. So we have a balloon. Now, it's supposed to be a spherical balloon, but looks a little more like an oval, but it has a radius r, and it has a certain volume of air that's inside of it. Now, air is being pumped in at the rate of 5 cubic inches per second. All right, so there is our graphic. Now, let's see, what are we given? So we're given Well, we're told that air is being pumped in at the rate. Okay, as soon as we see the word rate, that means we're given the derivative of something. Well, if you look, 5 cubic inches, the cubic inches, that's a volume. So we're given the rate of change of the volume. So we're actually given dV dt equals 5. Now what do we want to find? Well, we want to find the rate. Okay, so we need to find the derivative of something. The rate at which the radius of the balloon is increasing. Oh, okay, so we need to find dr dt when r equals 6. Now we need to find an equation that relates v and r. Well, the volume for a sphere, the volume formula for a sphere of radius r is this. Volume equals 4/3 pi times the radius cubed. If you look that up, that's the volume formula for a sphere of radius r. Now, the v and the r are functions of time t because they're changing. So now we need to find dr dt. Given dv dt is 5, we need to just differentiate this with respect to t. So we then have dv dt. Differentiating both sides with respect to t, we get this. All right, I just pulled the 4/3 pi out in front of the d dt. And so we then get v prime of t. Now dr dt, that's going to be 3r squared times r prime of t, right? Once again, you have to use a chain rule. Differentiate this with respect to r, 3r squared times dr dt, and that's right here. Now we need to solve for this piece right here. So we'll just take all of this and divide it to the other side, and we end up with, let's see, notice one thing here, the 3's actually cancel, that's nice, and so we're going to get, and then we need to find r prime when r is 6. Let's also notice the v prime, dv dt, we're given that that's 5, so we can replace this right here with a 5. And so we get that this is, let's just write that as 5 over. And then r prime of t when r equals 6. That's just going to be 5 over 4 pi. And that just equals 5 over 144 pi. And that is approximately 0.01105. I'll write that as. And that would have units of inches per second. That comes from the fact that our volume was changing at the rate of 5 cubic inches per second. And so our radius is then going to have units of inches, so dr dt will have units of inches per second. And if you could see those units coming out if you were to keep track of all your units as you were going through this. You would see inches per second coming out. We just didn't keep track of all of them. And that's our answer. All right, let's take a look at another problem. In this example, we have a 6-foot-tall man is walking down the street at the rate of 5 feet per second. He passes a light post that is 10 feet tall, and his shadow is cast in front of him. All right, two parts now. We want to find the rate at which the length of his shadow is increasing. And then part B, find the rate at which the tip of his shadow is moving. Well, all right, we need to draw a picture. Well, down here we already have a picture drawn for us. Let's make that a little bit larger. So here's our man right here, this stick figure right here, just that line. And he's walking down the street. Our lamp post is right here, right there's the light in our lamp post. The y-axis here is our lamp post, and right there's the light. And as he walks down the street, you see he is casting a shadow right here in front of him. So as he walks down the street, you see his shadow is cast in front of him, and he just keeps walking down the street like that. All right. So there's our graphic. Now let's label the variables. So let's say the man is at position X right here. Let's call that X, position X. And so that means that this distance is X right here. And let's label the length of the shadow as S. So this distance here we'll label as S. And then the lamppost is 10 feet tall, so that's already labeled for us right there as 10. Now let's see what we're given and what we want to find. I think we have everything labeled here that we can label. Let's see, the only thing here is that point right there. We could label that point as X plus S. All right, that's X plus S right there. If this distance is X, and that's S, that point on the x-axis is X plus S. We could label that. All right, now we are given, let's see, it says that he is 6 feet tall, okay. He's walking down the street at the rate of 5 feet per second. All right, so that tells us that dx dt is 5. And we want to find, let's see, well, we want to find two things here. We want to find the rate at which the length of his shadow is increasing. So for part A, we want to find ds dt. And for part B, we want to find ddt. It says the rate at which the tip of the shadow is moving. Now this tip is located at position X plus S, so we want to find ddt of X plus S. All right, so that's all our information here. The only thing I forgot to label here in our diagram was the man is 6 feet tall, so let's label this as 6 right there. All right. Now, looking back at this picture here, we have to find some equations that relate X and S. So this is going to be a case of similar triangles. So let's notice that we have some triangles here. We have this triangle, and we need to find another triangle that involves the X, which we can relate to this triangle. Well, we can label this triangle here as well. Let's color this one green. Now the red and the green triangle, they're similar triangles. And let's also notice that for the green triangle, that base is X, that's the same as this distance down here, and the height of this triangle is 4, because the 6 plus 4 gives you the height of the lamppost, which is 10. Alright, so now we have our triangles picked out, and what we can say is S divided by 6 is equal to X divided by 4 by similar triangles. So by similar triangles, And now this problem is actually pretty easy. Now all we need to do is move this 6 over to the other side, and then we can find ds dt in terms of dx dt. So then we get and so that's just 3/2 x. And now we can easily differentiate both sides, and we get s prime of t equals 3/2 x prime of t. And so therefore s of t, now we're given that dx dt is 5, so we can put this 5 right in place of the x prime of t, and so this is equal to 15, 3 times 5/2, that's going to be 15/2, or 7.5, and that's going to have units of feet per second as well, because x prime has units of feet per second, so it's going to be feet per second. And there we go, that's the answer to part A, 7.5 feet per second. Now for part B, we need to find d dt of x plus s. Well, for part B, well, that's just going to be d dt of x. So that's just going to be x prime of t plus s prime of t, and then we just have to add these together. So it's going to be 5 plus 7.5. And of course that is 12.5 feet per second. Okay, so the length of the shadow is increasing at the rate of 7.5 feet per second, and the tip of the shadow is moving down, or moving in the positive x direction at the rate of 12.5 feet per second. All right, and that's how you do this problem. So we just had to identify these similar triangles in this picture. Now let's let you try one. Now for this problem, I already have some of the graphic drawn down here. We have a conically shaped tank that has a top radius of 3 feet and a height of 10 feet. Water's being pumped in at the rate of 2 cubic feet per minute. We want to find the rate at which the water level is rising when the water level is 4 feet. Now this is a side view of our tank. The tank actually is three-dimensional. It looks something like this, really. Okay, it is three-dimensional. Now, the top radius of the tank is 3. The height or depth of the tank is 10. And water is being pumped in to the tank at the rate of 2 cubic feet per minute. And this is our water level down here, and it is rising. Now we want to find how fast the water level is rising when the water level is 4 feet. Now let's label some other things here. Let's see, let's say the depth of our water here, we'll call that h. And that's going to be a function of time t. So h is this distance from here down to the bottom of the tank. Let's say, let's call the distance from the midline here out to the outer edge r, where the water level is, so we'll call that r. And I think we have everything now. Oh, let's say the volume of the water, we'll call that v. That's the volume of the water level, the volume of the amount of water we have in the tank. And now I think we have everything in place. So let's see what we're given. We are given, now water's being pumped in at the rate of 2 cubic feet per minute. So that tells us the rate at which the volume of the water is changing. So we're given dV dt is 2. And we want to find the rate at which the water level is rising. So we need to find the derivative. Let's see, which variable is measuring the water level? Well, that's h. So we want to find dH dt when the water level is 4 feet, so when h equals 4. Now we need to find an equation then that relates v and h. Now this is the equation you might not be familiar with. For a right circular cone, the volume is going to be pi over 3 r squared h. That's the volume for a right circular cone looking like this, where you have a radius. This distance would be r, and your height would be h. And so just invert this, and that's going to be what our water looks like in the bottom of this conical tank. So this is the volume of the amount of water that we have in the tank. Now all the variables here are really functions of time t. So what we really have is v of t there. So we just labeled everything as being a function of time t. Now you might want to take it from here, pause the video here. You need to find dH dt. Well, now one trick here, you're going to need to figure out how to get rid of the r and write it in terms of h using similar triangles over here. Now assuming you try to do that, let's finish the problem now. So now we have to differentiate this equation and find dH dt. Now you see the problem here is that we have two variables here on the right hand side. We have an r and an h. It would be much better if we didn't have the r here. So we're going to try to get rid of this r by writing it in terms of h using similar triangles from our diagram over here. Now if you look over here, we have two triangles that are similar. We have this triangle and we have this triangle. Big triangle right here. Now the larger triangle has a height of 10, an upper distance of 3, and the smaller triangle has a height h, and the distance along this base of the triangle is r, and so we have this relationship then. So by similar triangles, we see that r over h equals 3 over 10. And so r is equal to 3/10 h. And we can substitute this in place of the r. Then we'll have everything in terms of only v and h, and then we can differentiate and find dH dt. So putting this in place of the r, what we get is this. So there we go. So v is pi over 3, 9 over 100, that comes from squaring 3/10. H cubed, that comes because we're going to have an h squared here coming from the r squared when we do this substitution, and h squared times h is h cubed. If we can simplify this a little bit, this will cancel with a 9 and just give us 3 right here. And now we can differentiate everything with respect to t. So we will then have that And now this side, when we differentiate h cubed with respect to t, that's just going to be 3h squared h prime, or 3h squared dh dt. So this is going to become and there we go. Now we have to solve for the dh dt right here. This is what we want to solve for. And so we just have to divide everything here to the other side, and what we're going to end up with is this. So we'll end up with h prime of t, that's dh dt, equaling, let's see, when we divide this to the other side, we're going to get 100v prime of t divided by 9 pi times h squared. And now we just have to substitute all our information in here. We are given that dv dt is 2, so we can put that in for the v prime. We want to find h prime when h is 4, so we can put that in for the h, and we'll have our answer. So let's see, so we're just going to put a 2 in here for that dv dt, and we're going to end up with h prime when h equals 4, when h equals 4. That's just going to be, now when I put 2 in for v prime, this will be 200 in the numerator. And simplifying that, we get 25 over 18 pi, which is approximately 0.44, and that will have units of feet per minute, because everything up here was given in terms of feet per minute in the original problem. And so there is our answer finally. So the water level is rising at the rate of 0.44 feet per minute when the water level is 4 feet deep. And so that concludes this lesson on related rates.